this lesson, we're going to start looking at equations with two variables, which is a topic we're going to be exploring for most of the rest of this term. We're going to start with a review. We're going to review solution sets to equations with one variable, solution sets to linear inequalities with one variable, and then we'll talk about this new type of equation with two variables and its solution set. And finally, we'll be focusing on linear equations with two variables, which is what Steve and Candace will come and talk more about later in this lesson. So let's review solution sets to equations with one variable. Here's an equation with one variable, z plus 5 equals 10. The solution's quite obvious. The solution is 5, and we wrote that as the set containing 5. We were also able to give a picture of this solution. So here I have a z number line with 5 indicated as the solution. Now here's another example of an equation with one variable. This is not linear. The absolute value of t equals 8, but we know what the solution set is. Both negative 8 and positive 8 make this equation true. Again, we can plot the solutions to this equation. Here I'm using a t number line, and I've plotted the point negative 8 and positive 8. So the solution set to an equation with one variable is the set of all numbers that make the equation true. So let's review linear inequalities with one variable. So here's the inequality, x plus 2 is less than 10. The solution set to this is the set of all x such that x is less than 8. Now here it really does help to draw a picture of the solution set. 8 is an upper bound on our solutions. We're looking at all numbers less than 8. So we represent this with drawing an interval. So the solution set to this inequality is an interval of real numbers, an infinite number of numbers in this interval that make the inequality true. So now let's look at solution sets to equations with two variables. So here's an example. X plus y equals 10. We have two variables, and it's an equation. But what is it telling us? It's basically, this equation just says the sum of two numbers is 10. So we should probably be able to think of some solutions to this equation. So let's just note down some possible solutions. For example, if x equals 10 and y equals 0, we'll get what we want. Then x plus y equals 10 plus 0, which equals 10. So I've just found a pair of numbers that sums to 10. Let's find a few more pairs. If x equals 0 and y equals 10, then the sum of x plus y is 0 plus 10, which equals 10. Let's find just a couple more. If x equals 5 and y equals 5, then x plus y equals 5 plus 5, which equals 10. One more. If x equals negative 10, I just had chosen all positive numbers, but I can sum up negative numbers as well. In this case, y would have to be positive 20. Then the sum of x plus y is negative 10 plus 20, which equals 10. Now you can see that I could probably do this all day. So we need to get a handle on which sets of numbers are indeed solutions. So how can we work with the observations we just made? We found 4 of many possible solutions. So here are my observations. And one of the things I notice is that each one of these solutions has an x and a y. So each observation can be written as an ordered pair, x, y. The solution set to an equation with two variables is a set of ordered pairs. So let's record such a set for this equation. So I'm going to start with some set brackets, and I'm going to throw in some of the ordered pairs I discovered while I was kind of playing around with the equation. From the first observation, I had x equals 10, y equals 0. I can throw that into my solution set. From the second observation, I have the ordered pair 0, 10. X equals 0, y equals 10. This third observation gives me the ordered pair 5, 5. And this observation gives me the ordered pair negative 10, 20. In fact, I can throw a bunch more in here as well. In fact, I could throw ordered pairs into the solution set all day. So I want some other way to kind of get a handle on the infinite number of ordered pairs that are going to live in this solution set. So here's the formal way to write the solution set. The solution set to the equation is the set of all ordered pairs, x, y, such that x plus y equals 10. Well, I don't know about you, but I'm finding that a little bit too abstract. It really just says x plus y equals 10, which is what I started with. So let's see if we can play with this some more and get a representation of the solution that's going to work a little bit better for us. So a table's a great way to consider some of the solutions to the equation. And when we look at the solutions in a table, we sometimes see patterns in the solution which can help us understand the solution set a little bit better. So let's put some solutions to our equation into a table. Now I'm just going to arbitrarily choose some values of x. I'm going to choose -1, -2, -1, 0, 1, 2, and 3. And I'm still looking for numbers that sum to 10. So -2 plus 12 sums to 10, -1 plus 11, 0 plus 10, 1 plus 9, 2 plus 8, and 3 plus 7. So when I look at the table, I actually do see a pattern. When I chose my values of x, I intentionally allowed the x values to increase by 1. That when I chose these values of x, it was kind of arbitrary, but I wanted to have a pattern in my x values. Because when there's a pattern in my x values, I can sometimes see a pattern in the corresponding y values. The x values are increasing by 1. The y values are decreasing by 1, which should make some sense in the context of this equation. The sum of two numbers is 10. So again, just to remind us that these are really not the solutions. The elements of the solution sets are ordered pairs. So let me just state the ordered pairs that correspond to these x and y values. So the solution set is a set of ordered pairs. Now my table doesn't show me the whole solution set. The table did help me establish a pattern I may not have seen earlier. So now, once I have a set of ordered pairs, I can use a graph, which is a great way to consider all the solutions to the equation. So what I'm doing is just looking at the ordered pairs, and I'm going to graph them in the coordinate plane. So I'm just going to graph these electronically. So here's my first ordered pair in the solution set, my next, my next, my next, my next, my next. And one of the things I notice is that all of these ordered pairs lie on a common line, that there's a pattern in the solution set. Now, if I look at this line, I'm going to find some other ordered pairs from the solution set that we talked about earlier. For example, here is the ordered pair 5, 5. We had thrown this in our solution set earlier. Here's the ordered pair 10, 0. We had thrown that in our solution set earlier. So one of the things that we can say about this picture of the solution is that any point on the line satisfies the equation, and any ordered pair that satisfies the equation lies on the line. So when we're looking at this graph, we're looking at a picture of the infinite set of ordered pairs that satisfies this equation. So although we couldn't write down the set in any way that really made sense to us, we can get a wonderful picture of the solutions to this equation. Now, before I proceed with a couple more examples, I just want to tell you that I worked through this rather quickly, and Steve is going to come in the second part of the lesson and talk a lot about creating these tables of values, and then Candace is going to talk about drawing the graphs from the table of values. So now you might be thinking, this is all well and good, but what does any of it have to do with the weather in Paris? Well, I can make a connection. Here is an equation in two variables. F equals 9/5 C plus 32. You're probably thinking, this is a formula. I've seen this formula before. This is the formula that allows us to calculate the Fahrenheit temperature given the temperature in degrees Celsius. But it's an equation. It's an equation in two variables, and we can consider it just like the equation we just worked with. So I'm going to start with a table. I have a table of values here. The first column are Celsius temperatures, and the second column are Fahrenheit temperatures. And these numbers came right from the equation. For example, in this first row, if I work with my equation, if C equals 0, then F equals 9/5 times 0 plus 32, which is 32. That explains the first row of the table. I'm just going to look at one more rather quickly. If C equals 100, then F equals 9/5 times 100 plus 32. Let's see, 5 goes into 120 times, so that's 180 plus 32, which is 212. So this is telling us that when the temperature is 0 degrees Celsius, the Fahrenheit temperature is 32 degrees. That's freezing, and then the boiling point, 212 degrees Fahrenheit, corresponds to 0 degrees Celsius. But we can generate solutions to this equation all day. So now what I've done is I've established some of the ordered pairs that satisfy this equation, and now I'd like to look at a graphical representation so I can get a picture of all of the solutions to this equation. So here I have C on the horizontal axis, temperature in degrees Celsius, and F, temperature in degrees Fahrenheit, on the vertical axis. When I look at the graph, I see some of these solutions we were just talking about. For example, here is the solution 0, 32. Here is the solution 100, 212. So now, if I take any Celsius temperature, like for example the temperature in Paris, I can calculate the corresponding Fahrenheit temperature using this graph. Let's look at another equation. This equation is an equation in two variables, C equals 300 plus 0.25 m. And this equation gives the cost, C in dollars, of printing a slogan on N water bottles. So let's look at a table of values. I've already filled it in, and one of the things we can do with this table of values is look for a pattern. So let's look at the table. I see that I've selected the values of N so that the number of water bottles is increasing by 200 in each row in the table. Let's look at what's happening to the corresponding costs. The costs start at 300, go up 50, go up 50, go up 50, go up 50, go up 50. So I'm certainly seeing a pattern in the table that I don't really see from the equation. So one of the things I notice is that when the total cost goes up by $50 for every 200 more bottles produced. And I'm going to look at this as a rate. And I can reduce this rate. If I cut both the numerator and denominator in half, I have $25 per 100 bottles. And I can divide 25 by 100, and that's $0.25 per 1 bottle. So I observed this pattern in the table, and I noticed that this 0.25 shows up in my original equation. That might be something I wouldn't have noticed if I hadn't looked at the solutions in a table. So now, let's make a table of the ordered pairs corresponding to our first 2 columns in our table, and let's look at a graph. So now I'm looking at the solution set to the equation C equals 300 plus 0.25n. Now, when I draw the line here, this is just to indicate that all of these solutions, which are in my table, lie on a common line. But one of the differences between this and the equation that represented temperature is that here I can't choose a number like 182.5 water bottles. That on this line, there's really not a point corresponding to that n value on the line in the context of the application. Mathematically, this line represents all the solutions to the equation C equals 300 plus 0.25n, but only some of the points on the line make sense in the context of the application. Candace is going to say a few more words about that in a later part of the lesson. So let's look at one last equation. X squared plus y equals 9. I'm going to start by creating a table. I'm choosing x equals -3, 0, and 3, and I chose these numbers just to make the arithmetic easy. So if x equals -3, we have x squared, so that's -3 squared, plus y equals 9. 9 plus y equals 9, so y has to equal 0. Let's look at the case where x equals 0. Then we have 0 squared plus y equals 9, or y equals 9. Now if I replace x with +3, what I'm going to end up with is very similar to what happened when I replaced x with -3. So when x equals +3, y will equal 0. So now I have a set of ordered pairs that I can graph. So let's create a graph, making some room for my graph paper. So I'm going to plot these 3 ordered pairs. So I have the point -3, 0, 0, 9, and 3, 0. And one of the things I noticed right off the bat is that these 3 ordered pairs do not lie on a common line. There's something different about this equation from the other equations we've considered. So let's finish up by talking about that difference. So an equation with 2 variables is linear if and only if its solution set graphs to a line. 3 of the equations we discussed are linear. X plus y equals 10, we looked at the solution set, it graphed to a line. F equals 9/5 c plus 32, and c equals 300 plus 0.25n. The last equation we discussed is nonlinear. When we plotted 3 solutions in the solution set to this equation, they did not lie on a common line. This is what it means to be nonlinear. Now here's the formal definition of a linear equation with 2 variables. It's of the form ax plus by equals c, with the condition that a and b cannot both equal 0. That's an idea we'll come back to a little bit later in these lessons. But let's just consider this definition in terms of the 3 linear equations we saw. In this example, a equals 1, b equals 1, and c equals 10. So this first linear equation we saw fits the form. Now here's our formula for converting Celsius temperature to Fahrenheit temperature, and it doesn't quite look like what we have there in the formal definition. So I'm going to change the names of the variables. And now when I change the names of the variables, I'm no longer talking about Celsius temperature and Fahrenheit temperature, but I still have an equation with similar characteristics. And in fact, I have an equation with the same solution set. Now this is not quite in the form given in the definition, but if I subtract 9/5 x from both sides of the equation, I can now see that this equation is in the form given in the original definition. A equals 9/5, B equals 1, C equals 32. Finally, here's our formula for cost. Again, I'm going to change the N in the C to X and Y, but again, we're no longer talking about water bottles and the cost of printing a slogan on the water bottles, but we have a similar equation with the same solution set. And if I want to talk about the values of A, B, and C, I'm going to subtract 0.25x from both sides. And I can see that the value of A is negative 0.25, the value of B is 1, and the value of C is 300. Now I did those kind of fast. We'll have plenty of practice with that in later parts of the lesson. Finally, here's our nonlinear equation, and we can see just from the form what's wrong. Our first term is x squared. A linear equation involves two variables, both to the first power. A linear equation won't have x squared or y cubed in it, just two variables such as x and y to the first power. So that concludes the first part of Lesson 13. Now I'm going to turn it over to Steve and Candace, who are going to spend more time going into detail on some of the ideas we looked at in this introduction.
Hello. Today I'm going to focus on finding solutions to linear equations with two variables. We're just going to solve a whole bunch of equations and fill in a whole bunch of tables. So a good place to start would be finding some solutions and then filling in a table. Then I'm going to find some special type solutions that we call intercepts. And I'm going to finish up by talking about some ways that you might tweak an equation before you set off for finding solutions. So let's begin by finding some solutions. Let's find the missing values in Table 1. So let's notice that in Table 1, we are given an equation. We're given the equation 2x plus 3y equals 12. And somebody's gone ahead and typed in some values for x in some rows and for y in other rows. And what we want to do is figure out the missing value for the other variable so that when we replace x and y with their respective values, the equation 2x plus 3y equals 12 is true. So a little more specifically, when x is 0, what we're going to do is we're going to solve the equation 2 times 0 plus 3y equals 12 for y. When x is 3, we're going to solve the equation 2 times 3 plus 3y equals 12 for y. You know what? I'm going to start with that row because there's another issue I want to talk about that I can address a little bit better with the row where x is 3 than I can with the row where x is 0. So, if x is 3, then we have 2 times 3 plus 3y equals 12. See how I've just replaced x with 3 in my equation. So let's go about solving this equation. The first thing we need to do is simplify the left side of the equation. 2 times 3 is 6. Now to isolate my 3y term, I need to subtract 6 from both sides of the equation. And when I do that, the left side of the equation simplifies to 3y, and the right side of the equation simplifies to 6. Now I need to use the multiplicative property of equality and divide both sides of the equation by 3. And when I do that, the left side of the equation simplifies to y, and the right side of the equation simplifies to 2. So I can see that in the equation 2x plus 3y equals 12, when x is 3, y needs to be 2. Now let me address this other issue that I mentioned before I started showing you this solution. In every solution we've done all term long, every time we've applied the addition property of equality and the multiplication property of equality, we've shown the step. And there's nothing wrong with showing the step. If you like, you can show the step forever. If it helps you to be successful to show the step, that's great. Show the step. A lot of people can find success without actually writing down those steps. So we are going to start to encourage you to try not writing down those steps by our not writing down those steps. So here's the step where I have explicitly subtracted 6 from both sides of the equation. I'm going to stop writing down that step and just show the result. Here's the step where I've applied the multiplication property of equality. I'm going to stop writing down that step and just show the result. Now again, I'm not saying that you have to stop writing down those steps, but I do encourage you to at least try and see if you can be successful without writing them down. If you can, great. If you can't, that's great too. Just continue writing them down because we want you to be successful. But for my part, let's say bye to those 2 steps because we're not going to be showing them very often anymore. So we can see now that when x is 3, y needs to be 2 to solve the equation 2x plus 3y equals 12. So I'm going to go ahead and put the y value of 2 into my table. So let's go back to the first row and start filling in the other values. When x is 0, we have the equation 2 times 0 plus 3y equals 12. Simplifying the left side of the equation, we just have 3 times y equals 12. When I apply the multiplication property of equality, I need to divide both sides of the equation by 3. When I do that, on the left, I'm just left with y, and on the right, I'm left with 12 divided by 3, which is 4. So when x is 0, y is 4. When y is 0, we have, let's see, 2 times x plus 3 times 0 is 12. 3 times 0 is 0, so the left side of the equation simplifies to 2x, and that still equals 12. When I divide both sides of the equation by 2, the left side simplifies to x. The right side simplifies to 12 divided by 2, which is 6. So x is 6 when y is 0. Let's see, we already did the 3, 2 row, so let's jump down to when y is -5. We have, let's see, 2 times x plus 3 times -5, that equals 12. 3 times -5 is -15, so 2x minus 15 is 12. When I add 15 to both sides of the equation, the left side of the equation simplifies to 2x. The right side of the equation simplifies to 12 plus 15, which is 27. And when I divide both sides of the equation by 2, I'm just left with x equals 27 over 2. 2 more rows. What about when x is 3 halves? When x is 3 halves, we have, let's see, 2 times 3 halves plus 3y equals 12. 2 times 3 halves is the same as 2 times 3 times a half. 2 times a half is 1. So the first term on the left just simplifies to 3. So we have 3 plus 3y equals 12. Subtracting 3 from both sides of the equation, on the left we're left with 3y. On the right we're left with 12 minus 3, which is 9. And if we divide both sides of the equation by 3, we have y equals 9 divided by 3, which is 3. One more. If y is 514, we have, if you're wondering why I wrote if this time instead of when, I just felt like mixing it up. Some people like the word when, some people like the word if, so I like to accommodate both types of people. So if y is 514, what do we have? We have 2 times x plus 3 times 514. That equals 12. 3 times 514 is going to be, 1,500 plus 30 plus 12. So that is 1,542. So we have 2x plus 1,542 equals 12. When we subtract 1,542 from both sides of the equation, we get the equivalent equation, 2x equals negative 1,530. So when we divide both sides of the equation by 2, on the left, we're left with x. On the right, we're left with a negative number. Let's see, 2 goes into 15 7 times with 1 left over. So 2 goes into 13 6 times with 1 left over. And 2 goes into 10 5 times. So I think we get negative 765. Yes, we do get negative 765. Now remember, none of these numbers in the table are actually solutions to the equation, but the pairs of numbers in each row do directly imply actual solutions to the equation. For example, x equals 0, y equals 4 implies the order pair 0, 4, and the order pair 0, 4 is the actual solution. So I'm going to tack on an order pair column here and focus on the fact that we use the table to help us calculate the solutions, but the actual solutions are the ordered pairs. Now I'm going to talk about a couple of special solutions that we call intercepts. Let's start with a definition. For a linear equation of the form ax plus by equals c, the x-intercept is the solution to the equation of the form x sub 0, comma 0, and the y-intercept is the solution to the equation of the form 0, comma y sub 0. Now, a few things about this definition before I move on and show you some examples. The symbol x sub 0 is frequently referred to as x naught, and I'm pretty sure you'll hear me, Candace, or Ann say x naught from time to time, so you need to know that that's just another way of saying x sub 0. Another thing that you want to keep in mind is that the x-intercept is a point or an ordered pair that has a y-coordinate of 0. And the y-intercept is a point or an ordered pair that has an x-coordinate of 0. And that's the way I have that information stored in my noggin. So you might try practicing saying to yourself, the x-intercept is the point with a y-coordinate of 0. And the y-intercept is the point with an x-coordinate of 0. If you say that to yourself several times, literally out loud, you'll finally say, you know what, I got it, it'll stick. So I suggest you try that. So let's answer this question. What are the x and y intercepts of the line with equation 2x plus 3y equals 12? I need to find 2 points. So I think I'm going to introduce a table to kind of help me organize my thoughts. And I'm also going to move the table so that once my thoughts are organized, I'll have a place to write my conclusion. Now, I think I just said that the x-intercept is the point that has a y-coordinate of 0. Another way of saying that is the x-intercept is the ordered pair that has a y-coordinate of 0. So I am going to go ahead and indicate a y value of 0 in the first row of the table. The y-intercept is the point that has an x-coordinate of 0. So I'm going to use the second row to figure out what y needs to be when x is 0. Now I think I can do both of these figurings in my head. When y is 0, we get the equation 2 times x plus 3 times 0 equals 12. That simplifies to 2x equals 12. Well, what number do I multiply by 2 and end up with 12? That's 6. When x is 0, we get the equation 2 times 0 plus 3y equals 12. 3y equals 12. I guess y must be 4, because 3 times 4 is 12. So far, I haven't written down the actual solutions. I certainly have clearly implied them, but the actual solutions are ordered pairs. They're the ordered pairs 6, 0, and 0, 4. In a little while, we're going to stop including this ordered pair column in our table, but we'll never stop including ordered pairs when we write down x and y intercepts because they are explicitly ordered pairs or points. So I am going to go ahead and write a conclusion to the question. The x-intercept is the ordered pair or the point 6, 0. The y-intercept is the ordered pair or the point 0, 4. Let's see another example of this. What are the x and y intercepts of the line with the equation y equals 2x minus 3? Well, looking at this equation, I can see that if I replace x with 0, I'm just left with y equals negative 3. There's really no solving to do whatsoever. The point that you get when x is 0 is called the y-intercept. So without doing any work, I think we can just go ahead and say that the y-intercept is the ordered pair 0, negative 3. I said point before. I deliberately said ordered pair there because I want you to get established that these are two phrases for the same idea. Now, the x-intercept, that's the ordered pair that I get when y is 0. When I replace y with 0, the equation that I get is 0 equals 2x minus 3. Now, you might be able to solve that in your head. And if you can, that's excellent. Just go ahead and write down what the x-intercept is. If it helps you to show some work to figure it out or to do some work on some scratch paper to figure it out, that's excellent. Go ahead and do that. You want to do what helps you to be successful. I think I am going to show a little bit of work to figure this out. When y is 0, we have the equation 0 equals 2x minus 3. When I add 3 to both sides of the equation, we have 3 equals 2x. And when we divide both sides of the equation by 2, we have 3 over 2 equals 2x over 2, which is x. So I can see that the x-intercept is the point 3/2, 0. If it helps you to do that work on your paper, do it. If you can do it in your head, do it. Do what works for you. Let's leave this x and y intercept idea behind for a little bit, and let's go ahead and fill in another table. Y equals 2x minus 3. I've been asked to find the value of y for several values of x. Before I set out to do this, I am going to notice that there's a pattern in the x column. Every time I move from one row to the next, x goes up by 1. Negative 2 plus 1, negative 1. Negative 1 plus 1, 0. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. So let's see what y is at those 6 values. Well, when x is negative 2, y is 2 times negative 2 minus 3. That's negative 4 minus 3, which is negative 7. When x is negative 1, y is 2 times negative 1 minus 3. Negative 2 minus 3 is negative 5. When x is 0, y is 2 times 0 minus 3. 0 minus 3 is negative 3. when x is 1. Y is 2 times 1 minus 3. 2 minus 3 is negative 1. I think I'm going to pause and pick up on this pattern idea. Let's see if there's any sort of pattern emerging in the y column. It looks to me like there is. If I take negative 7 and I add 2, I get negative 5. If I take negative 5 and I add 2, I get negative 3. If I take negative 3 and I add 2, I get negative 1. I bet you the next two numbers in my y column are going to be negative 1 plus 2, which is positive 1, and 1 plus 2, which is 3. Let's check. When x is 2, the value of y is 2 times 2 minus 3. 4 minus 3 equals 1. When x is 3, the value of y is 2 times 3 minus 3. 6 minus 3 is 3. So our pattern worked. Now, I want to make another comment about this table. I want you to know that this is the last time you're going to see me, or probably Candace or Ann, actually doing calculations inside the table. The only reason I did it in this one example was I wanted to make sure that you saw where these numbers, negative 7, negative 5, negative 3, etc., came from. One other thing that I want to talk about is the fact that we saw this pattern that every time x went up by 1, y went up by 2. And I'm going to make the observation that if I take this change in y, which is 2, and I divide it by the change in x, which is 1, look what number I get. I get the number 2, which is the coefficient on x. It turns out that when you have a linear equation that's solved for y, the coefficient on x has really important implications about the behavior of the ordered pairs that satisfy the equation. The coefficient on x is called the slope, and lesson 14 is going to be all about slope. I'm just giving you a little preview about the importance of this coefficient on x. Now, let's remember that technically none of the numbers we've written down are solutions to the equation. Solutions to equations with two variables are ordered pairs. These numbers imply the ordered pairs that are the solutions. The solutions are the ordered pairs negative 2, negative 7, negative 1, negative 5, 0, negative 3, 1, negative 1, 2, 1, and 3, 3. A few more examples so I can talk about some ways that you might tweak an equation before finding solutions. Let's find the solution suggested in this table. So we have the equation 6x minus 2y equals negative 8, and we want to find 6 values of y that correspond to 6 given values of x. Now let's think what happens if I just dive right in. If I replace x with negative 4, I'm going to have to solve the equation negative 24 minus 2y equals negative 8. If I replace x with negative 2, I'm going to have to solve the equation negative 12 minus 2y equals negative 8. Hopefully you can see where I'm going with this. I'm going to have to solve 6 equations. I have a different strategy. I only want to solve one equation. And the one equation I'm going to solve is this literal equation that has both the letters x and y in it. Remember that when you have an equation that has 2 or more variables and you want to solve that equation for one of the 2 variables, you call the equation a literal equation. So I'm going to go ahead and solve 6x minus 2y equals negative 8 for y. So I'm starting with 6x minus 2y equals negative 8. I want to isolate y. I'll begin by subtracting 6x from both sides of the equation. That gives me negative 2y equals negative 8 minus 6x. Now to completely isolate y, I need to divide both sides of the equation by negative 2. Now the right side of the equation is going to be a little bit complicated, so I think I'm going to take a few steps to simplify it. On the left, I'm just left with negative 2y over negative 2, which simplifies to y. On the right, I'm left with the fraction whose numerator is negative 8 minus 6x and whose denominator is negative 2. The first thing I'm going to do to try and simplify this formula is I'm going to break the right side into two separate fractions. Y can be written as negative 8 over negative 2 minus 6x over negative 2. Now, put your concentration cap on here because I'm going to kind of talk us through this. Negative 8 divided by negative 2, when you divide a negative by a negative, the result is positive, and 8 divided by 2 is 4. 6x divided by negative 2. If I take 6 divided by negative 2, the result is negative 3. So 6x divided by negative 2 is negative 3x. But that's being subtracted. And subtracting a negative is the same as adding a positive. So my formula for y is y equals 4 plus 3x. Look at how much easier it is going to be to fill in my table. I think I can do it in my head. When x is negative 4, y is 4 plus 3 times negative 4. 3 times negative 4 is negative 12. 4 plus negative 12 is negative 8. Now, if that's a little tough for you to do in your head, that's okay. Get out some scratch paper and work it on the scratch paper, because we just want you to do what works for you to be successful. When x is negative 2, y is 4 plus 3 times negative 2. That's 4 plus negative 6, which is negative 2. When x is 0, y is 4 plus 3 times 0. Well, that's just 4. When x is 2, y is 4 plus 3 times 2. 4 plus 6 is 10. Let's pause and look for a pattern. In the x column, every time we go from one row to the next, x is going up by 2. Negative 4 plus 2 is negative 2. Negative 2 plus 2 is 0. 0 plus 2 is 2. X is going up by 2's. What's happening to y? Well, to get from negative 8 to negative 2, I think we need to add 6. And if we add 6 to negative 2, we get 4. And if we add 6 to 4, we get 10. I see our pattern. Every time x goes up by 2, y is going up by 6. I just bet you the next two rows are 16 and 22. Now, this is a new idea, so let's make sure that these values are correct. When x is 4, we have 4 plus 3 times 4. 4 plus 12 is 16. When x is 6, we have y equals 4 plus 3 times 6. 4 plus 18 is 22. Our pattern worked. And one more word about the pattern. Y was going up by 6. The change in y is 6 when the change in x is 2. 6 divided by 2 is the coefficient on x when we solved for y. That number is called the slope. And we're going to be talking about the slope a whole lot in future lessons. I'm just giving you a preview. Now let's remember, these numbers merely suggest points that are actual solutions, ordered pairs that are actual solutions. The actual solutions are the ordered pairs minus negative 4, negative 8, negative 2, negative 2, 0, 4, 2, 10, 4, 16, and 6, 22. So I've now covered up the numbers that we use to determine our solutions, but ironically, it turns out that pretty darn quick, those are the only two columns that we're going to show, are the numbers that imply the solution. Let's look at this example. In this example, I've done a lot of work ahead of time. We started with the equation 5x plus 3y equals 15. And what I did ahead of time was I went ahead and I found a formula for y in terms of x. And I think I can show you pretty quickly where that formula came from. If I take 5x minus 3y, 5x plus 3y equals 15. If I subtract 5x from both sides of the equation, I have 3y equals 15 minus 5x. And if I divide both sides of the equation by 3, I have y equals 15 minus 5x over 3. So that's where that formula came from. Then I've gone ahead and I've replaced x with 5 different values. For example, if I replace x with 5, in the numerator, I'm going to have 15 minus 5 times 5. That's negative 10. So for the fraction in its entirety, I'm going to have negative 10 over 3. If I replace x with 6, in the numerator of y, I have 15 minus 5 times 6. 15 minus 30 is negative 15. Negative 15 divided by 3 is negative 5. So hopefully you're understanding where all these numbers come from. Now the observation I want to make is that in 3 of my rows, the y-coordinate turned out to have a fractional part. But in 2 of my rows, the y-coordinate turned out to be integers. And what Candace is going to be showing you after I'm done is plotting solutions to equations with 2 unknowns. If you're working with a grid that has any sort of integer scale, you're going to get a much more accurate graph if you plot points where both coordinates are integers. So it's always a good idea when possible to come up with a strategy so that both coordinates of your points in your table are integers. Let's develop such a strategy. So we want to come up with a strategy that allows us to find ordered pairs x and y where both coordinates are integers in our solution. I'm going to begin by solving my equation for y. So I have 5x plus 3y equals 15. As we saw earlier, when I subtract 5x from both sides of the equation, I have 3y equals 15 minus 5x. And then when we divide both sides of the equation by 3, we have y equals the quantity 15 minus 5x over 3. That's the form of the formula that I used on the previous screen, but I'm going to go ahead and break this up into 2 fractions because it turns out that when you're looking for integer pairs that are solutions to the equation, it's easier to find them sometimes if you break the formula into 2 terms. So I'm going to go ahead and say that y is 15 over 3 minus 5x over 3, and make the observation that 15 over 3 is just 5. Now I'm looking for values of x that's going to result in an integer value of y. Here's the ticket right here. If I can take x values that are evenly divisible by 3, the fraction's going to be out of there. So when I pick values for x in my table, I'm going to pick values of x that are evenly divisible by 3. For example, negative 6, negative 3, 0, 3, and 6. So here I've gone ahead and made up a table that has my formula for y as the column heading in the y column. I can see that what I need to do is choose values of x that are evenly divisible by 3 if I want to end up with integer values for y. So let's go ahead and pick some values of x that are evenly divisible by 3. For example, negative 6, negative 3, 0, 3, and 6. I think the first computations are complicated enough that it'd be worth doing a little bit of scratch work to figure them out. So when x is negative 6, we have y is 5 minus 5/3 times negative 6. So this is going to be 5. In my product here, I'm subtracting a negative, so the result is going to be the same as adding a positive. 3 goes into 6 2 times. 5 times 2 is 10. So y turns out to be 15 when x is negative 6. When x is -3, we have y equals 5 minus 5/3 times -3. That's 5 plus 3 goes into 3 one time, so it's 5 plus 5, which is 10. I think I can do x equals 0 in my head. Y is 5 minus 5/3 times 0, which is 5. Now, I have a pattern in my x column. In my x column, x is going up by 3s, row by row. It turns out when you have equations that graph to a line, if you have this incremental pattern for your x values, there will always be an incremental pattern for your y values. And I can see in this table that the incremental pattern for y is that y is going down by 5 every time x goes up by 3. Let's see if we can see that in the formula. Look right here, minus 5/3. Y is going down by 5 every time x goes up by 3. That's this idea of slope that we're going to focus on so much in lesson 14 and even lessons after that. But now that I've made that observation, I'm just going to go ahead and write down what the next two y values are. The next two y values are going to be 0 and -5. And let's remember one last time that these numbers aren't the solutions. The solutions are ordered pairs. -615 is one solution. The point -310 is another solution. The ordered pair 0, 5 is another solution. But since those ordered pairs are directly implied by the table that I've produced, I'm just going to assume that the person looking at the table knows that we're actually trying to communicate ordered pairs. One last example, and then I'm out of here. Let's get back to this intercept idea. What are the x and y intercepts of the line with the equation 5x plus 3y equals 15? Now, before I start writing, I am going to think, am I going to be able to do this in my head? If I replace x with 0, am I going to be able to solve for y in my head? Well, I am, so I'm going to go ahead and do that. Similarly, when I replace y with 0, am I going to be able to solve for x in my head? And again, I am, so I'm going to go ahead and do it that way. If you feel more comfortable showing the work or doing some work on the scratch paper, that's excellent. Do what you're comfortable doing. Let's see. Let's start with the x-intercept. The x-intercept is, it's the ordered pair that has a y-coordinate of 0. When y is 0, we get the equation 5x plus 3 times 0 equals 15. 5x equals 15, x must be 3. So the x-intercept is the ordered pair 3, 0. The y-intercept is the ordered pair that has an x-coordinate of 0. When x is 0, we get 5 times 0 plus 3y equals 15. Y must be 5. So the y-intercept is the ordered pair 0, 5. The y-intercept is the point 0, 5. And speaking of points, Candace is going to be plotting a whole lot of them in her part of the lesson.